Looks like it's recording. So yeah, we're going to see if this works today. This is just an experiment, and if it does work, then maybe I'll start re-recording some of those ones that I put up before. But for now, for the air conditioning stuff, we're going to start with this chart. And you guys, you may recognize this chart from some of the stuff you did in level 3. But what we're showing here is the relationship between temperature and what happens with the liquid that we're very familiar with, right? Water. If you take a look at this graph here, it's showing us sort of the temperature progression of water as it goes from ice to a liquid to a vapor. And we're going to look at this and then kind of relate this to what happens inside of the refrigeration loop. Okay, so there's a couple of numbers that we want to focus on first. BTUs. Okay, so when we're talking about BTUs, British thermal units, what exactly is one British thermal unit? Does anybody remember?
The amount of energy needed to raise 1 pound of water 1 degree.
1 degree Fahrenheit, yeah. So this graph that we're looking at here is representing the amount of heat energy it takes to affect the temperature of 1 pound of water. Okay, now, I know that those are old school standard units of measure. It's not metric, but it just works, and this is kind of the language my brain works for this stuff. Okay, so taking a look at the temperature in Fahrenheit over here, 32 degrees up to 212 degrees. The amount of degrees of temperature change, if you do a little bit of math, is 180 degrees Fahrenheit, right? And that's where that 180 BTU number came from. It takes 180 BTUs to get 1 pound of water from where it goes from a solid to a liquid, all the way up to where it goes from a liquid to a gas. Okay? The amount of heat energy it takes to get that liquid to turn into steam or to get that liquid to turn into a solid, it takes a lot more than 1 BTU per pound to get it that next degree. Okay, I think we all know that if you take a pot of water, put it on the stove and boil it, the temperature of the water in that pot is going to stay the same as it boils, right? That doesn't mean we're not putting heat energy into it anymore. We're still putting heat energy into it, but the temperature is not changing. Instead, we're using that heat energy to get it to change phase, right? Go from a liquid to a gas. That takes energy. As a matter of fact, it takes 970 BTUs to make that happen. So that means it takes a lot of heat energy to go from a liquid to a vapor. We can absorb a lot of heat is another way of looking at that. And when it comes to a refrigeration system, this is exactly what we're doing. If you think about it, the evaporator, which is one of the heat exchangers, we use it to soak up heat and turn liquid into vapor, liquid refrigerant into vapor. Okay. The latent heat of vaporization for water is 970 BTUs per pound. Okay. Can one of you guys, some of you guys got your computer open there, just do me a quick favor and see if you can figure out what the latent heat for R134A is. Somebody just Google that for me real quick. I'm curious what that number is. I know it's lower than water, but it is an interesting thing to see.
For what?
For R134A, normal refrigerant. Does it give you like a BT? 93.4 BTUs per pound? Dang. That's quite a difference from water. And yet it still does the job pretty good for us, doesn't it? Okay. But that means that you can move 93.4 BTUs per pound. But even on a system that's only got 2 pounds, we're pumping that pound really fast in circles inside that system, right? That's why it works. Okay. What's interesting here is if we look at what happens with this liquid, and still looking at water, if you take that 1 pound of water and you start warming it up beyond the point where it changed state, all you're doing is you're just warming up the vapor. We call that superheating. Okay, and the same thing can happen in the refrigeration system where the liquid refrigerant is now boiled off into a vapor inside the evaporator. That's the heat exchanger inside the cab. And then we start warming up the vapor. However, once we start warming up vapor, we're basically back to that 1 BTU per pound kind of a thing. Okay, it doesn't really carry, or it doesn't allow us to absorb as much heat energy. Let's put it that way. Over on the other side, for the subcooling, if I take that evaporated or that vapor refrigerant and I run it through a condenser, what we're trying to do is we're trying to strip that heat energy back out of it, right? And when we get that heat energy out of it, now it goes from a vapor to a liquid, changes state. We got a whole bunch of heat energy out. And then if I start cooling down the liquid, again, it's kind of pointless. It's a waste to spend a whole bunch of time cooling down the liquid, because we're back to that, in theory, 1 BTU, or 1 BTU per degree Fahrenheit that we cool it down. When it comes to superheat, you don't really want to have a huge amount of it happening, okay? Because it's not a very efficient way of transferring heat. When it comes to subcooling, this happens in the condenser. Again, it doesn't really matter how much happens as long as some did happen, indicating that the phase change happened. Does that make sense? Okay. So I think the next thing we're going to do here is we'll put together just a basic diagram of the AC loop here. And we will start with the pump. Okay. And try that again. Okay, so here we got the pump. This pump is what we call the compressor, right? And what does that compressor move? Does it move gas or liquid in the system? It's going to be gas, so I'm going to leave that triangle open. Okay. We are going to have, I'm going to move this over a little bit so I got some more room. Okay, so we're going to have come on now. The first part of the system here, and it's going to feed this thing. Okay, that heat exchanger. What do we call the one that the compressor feeds?
Condenser.
That's the condenser. Okay, so that condenser, take that, put it right there. We'll have the line coming out of the condenser and then heading off towards. Well, there is a restriction in the system. That's your thermal expansion valve, usually. What other type of restrictor do we sometimes use in the system? An orifice tube would be the other option. We're not going to look at that right now. We're going to look at the expansion valve style. So the refrigerant that leaves the condenser, it goes to the expansion valve, but it has something that it goes to first. It's like a little storage tank that also has a filter. The receiver dryer, yeah. So that receiver dryer is going to be down here, and it's basically just a little tank. We're going to put the refrigerant in it. We're going to take the refrigerant back out of it, and then in between, there is a filter. There's a desiccant, there's a filter, and the receiver dryer is going to act like a bit of a storage tank for us. Okay. So from there, we're going to head up to the other heat exchanger. And this one is our evaporator, right? And then up and over back into the pump. Try that again. There we go. And then, like I said, we do have a restrictor in here. That restrictor we're going to call the receiver dryer, and it's going to fit over here somewhere in between the receiver dryer, and the evaporator. Okay. Your expansion valve is a variable restriction. It's something that we can control. Okay. So what we'll do now is we'll just go ahead and designate these compressor, condenser, evaporator, TXV stands for thermal expansion valve, and then receiver dryer. Okay. So those are the major components of any refrigeration system. The expansion valve, one thing that we should draw on there is the fact that it's effectively thermostatically controlled by the temperature of the refrigerant coming out of the evaporator. Okay, so we'll go ahead and we'll show a temperature sensing bulb over here. Okay, and then we're going to have that bulb come over to the expansion valve. And that temperature sensing bulb, what it does is if the evaporator is, if there's too much superheat in the evaporator, that means the outlet of the evaporator is too warm. That means we put liquid in, we boiled it off, and we started heating up that vapor. That's not what we want to have happen. Okay, so if the outlet of the evaporator gets too warm, that temperature sensing bulb is full of refrigerant. The refrigerant pressure is going to go up because the temperature went up, right? And that pressure is used to open up the expansion valve. And when the expansion valve opens, it lets more refrigerant in. If we flood the evaporator with too much refrigerant, it's going to get too cold. The outlet temperature of the evaporator goes down, the refrigerant inside that little bulb collapses, the pressure goes away, and that pressure is what was holding the expansion valve open. Now you have an expansion valve that starts to throttle back. So the line, going back here, the line that goes from the expansion valve to this little bulb here is going to be filled with refrigerant. The same type of refrigerant is what we're using in the system. Okay. The other thing about that bulb is it has to be insulated so that the only temperature that it's sensing is the temperature of the outlet of the evaporator line. All right. Now, for the most part nowadays, this is kind of irrelevant because that thermal expansion valve is the H-block style where the bulb is right inside of the H-block. Okay. There's another style where you have an external capillary tube in a bulb. That style, you have to insulate the capillary tube in the bulb so that outside temperature doesn't interfere with the system. If that bulb got warm because it was picking up heat in the air handling unit of that piece of machinery, that would warm up that refrigerant, and that would cause the expansion valve to open, and it could cause the evaporator to flood. And if you flood the evaporator, one of two things can happen. You might either end up with a frozen evaporator, where all of the water that it was condensing out of the air in the cab starts to freeze on the evaporator core, or you might end up flooding the evaporator to the point where you start liquid slugging the compressor, and that's really bad. Okay. Now, when you guys did your AC training in previous levels, you probably discussed that this system kind of has 4 different quadrants to it, right? And those quadrants have different things happening in them. So, for instance, over here, we might have the compressor. If we think about what the state of the refrigerant is, what is it? It's a gas, okay? If we think about what the temperature is, if I was to use a thermometer and measure the temperature coming out, would it be really hot or really cold? This would be hot. Okay. If I was to look at the pressure, is this likely going to be the spot where the pressure is more or less the highest in the system? Well, yeah, because it's coming right out of the compressor. Okay. So a high pressure, high temperature gas. Okay. What about the amount of heat energy in that refrigerant? It's going to be high BTUs, yeah. Okay. So it's a gas, high pressure, high temperature, high BTU. Okay. If we come down here and we run it through the condenser, what happens? Okay. So we're going to try and remove heat energy from that vapor. Okay. And when you do that, if you get enough heat energy removed from the vapor, what happens to it? state change. So we're going to try and turn it into a liquid here, right? Okay. Now, are we really trying to achieve a huge amount of temperature change here, or are we just trying to get the phase change to happen? Phase change. So there is going to still be, like, the temperature here is irrelevant. It might be pretty warm. It might have cooled off a bit. It just depends on what the ambient temperature is relative to what's happening in the system. But let's go medium to high temp. The condenser, especially on the systems that you guys are likely to be working on, fairly small. This is not some huge industrial chiller. So the pressure drop across that heat exchanger is pretty negligible. So I would say it's still high pressure, right? If we've done our job correctly, what will have happened to the heat energy? It's going to be low. So what's interesting is, even though the temperature might seem high, the BTU content of that refrigerant is going to be relatively low. Okay. Come over to the other side of the system. We're going to run that refrigerant through the expansion valve. As it goes through the expansion valve, it's still a liquid. Okay, in order to turn it from a liquid into a vapor, what do we have to do? We got to boil it, right? So putting it through the expansion valve, the only reason we do that is to reduce the pressure. Okay. Now, with anything, when you change the pressure on it, you also change its boiling point, right? Okay. Water, it's the exact same. Why do you think you stick a vacuum pump on an AC system before you charge it with refrigerant? To suck the air out? Well, yeah, but way more importantly than sucking the air out is sucking the water. You can suck the air out of an AC system in probably like 5 minutes. So why do you leave the vacuum pump on for 15 minutes? Give the moisture time to boil off, right? But the reason that water will boil off inside the AC system is because we reduce the pressure. The same thing happens to the refrigerant here. If you reduce the pressure, you end up reducing the temperature. Low temperature, low PSI, and still low BTU because we didn't soak up any heat yet with it, right? And then coming up over here, if the expansion valve is doing its job properly, that would mean that coming out of the evaporator, that's right there in the name, we should have evaporated it. Okay, we should have vapor. Okay. The temperature, if I feel the outlet of the evaporator, it's going to be ever so slightly warmer than what the inlet was. All right, just a little bit warmer, but it's still going to feel cold, right? The pressure, even though that liquid boiled into a vapor, again, the pressure, it's not really going to have changed that much. We didn't heat it up enough to cause a huge increase in pressure. But there's going to be really high BTU. And the reason for the high BTU is because we boiled that liquid into a vapor and soaked up a huge amount of heat energy, which is exactly the point of the system, right? Okay. So here we do have our system. Hold this down a bit so we got some room to draw around it some more. And we're going to add a couple more features to this. Okay. So one's going to be a switch on the low side. Okay. And one is going to be a switch on the high side. Now the low side switch, it might be on the low side. The low pressure switch might also be built into the same switch package and stuck on the high side. Okay. So what I'm going to do is I'm going to kind of explain what pressure these would normally go on and off at, and then talk about why they're installed there. So the high pressure switch, usually this one will cut off somewhere around 400 to maybe 450 psi. The low switch, probably somewhere between about, these vary, you can get them in different ranges, but let's say somewhere around maybe 10 psi. Like I've seen these as low as 5 psi, I've seen them as high as about 25, 30 psi, okay? It just depends on what side of the system they're mounted to, okay? But why have a low switch? Well, if your low switch is on the low side of the system, it's there for two reasons. It's there to switch the compressor off when the low side pressure gets too low. It's there to keep the compressor from turning on when there is no pressure in the system at all. Give me two reasons why there'd be no pressure in the system. A leak, so there's nothing in there, for sure. And what's the other reason there wouldn't be any pressure in the system? No. Well, that would be the same thing as a leak and a low charge, yeah. What do you mean by that?
Like the TXV or the receiver dryer?
Oh, okay, yeah. So basically you're saying that there's no refrigerant on the low side, so that's why it's pulling it down. And you know what? You're not wrong. It could be that. So then let's make it three things then. Because what if it's just really cold outside, guys? What happens to the pressure of refrigerant when you heat it up? It goes up. What happens to the pressure when you cool it off? It goes down. Did you know that the atmospheric boiling points of R134A is about minus 20 degrees Celsius? So if you went outside on a cold winter day, let's say minus 25 or something like that, you could crack open a tank of 134 and just pour it into a pail, and it wouldn't boil. It'd just be like water, okay? So what that tells us is if the pressure gets low because the temperature is low, let's say that refrigeration system is sitting in a machine in the middle of winter, if you turn the compressor on and there's no refrigerants moving in the system because there's no vapor in the system, that's not good for the compressor. Do we know why? Because the compressor is lubricated by the oil that's being carried around with the refrigerant, right? Just like a two-stroke gas engine. So yeah, you're going to destroy your compressor because there's no lubricant. So that means that low switch, its other job is to protect the compressor when it's cold outside, because there's no need to run it when it's that cold. There's no need to use the refrigeration portion of the system when it's that cold, okay? You've got to make sure that we're at least warm enough so that there's vapor in the system to carry lubricant through the compressor. The high side switch, what's the purpose of that one? So if your high side pressure gets too high, we just shut the compressor off instead of blowing something up in the system. Okay, why would the high pressure be that high? Okay, so if you say a blockage, I agree with you. Let's be more specific. What kind of a blockage? Plug TXV? Nope, absolutely not. And you know what? The reason why a plug TXV won't cause higher than normal high side pressure, actually it's so counterintuitive, it causes the opposite. It causes lower than normal high side pressure. A block TXV does not cause higher than normal high side pressure, okay? If you have the right charge, I better put that in there because I've actually seen it where a block TXV did cause the high side to spike like crazy, but that's because somebody kept adding refrigerant because they thought that a lack of refrigerant was the problem, okay? That was not the issue. So anyways, a block TXV, as long as the system has a proper charge in it, what's going to happen is it just won't let refrigerant through the low side. Okay. And if it doesn't let refrigerant through the low side, that means that all of the liquid refrigerant in the system is going to stack up on the high side. We're going to end up filling up the receiver dryer. Okay. And we're going to fill up the line going back to the condenser, and all of the liquid refrigerant is going to condense, and it's going to sit there at the very bottom of the condenser and in the receiver dryer. Okay. And then what happens is we're not pumping any refrigerant in the system, so any of the refrigerant that's sitting in a condenser as a vapor, we're actually going to start stripping more and more heat out of it. There's going to be more subcooling. And as you start pulling heat out of the refrigerant, as it starts to cool down, what happens to its pressure? It goes down. Okay? It's really interesting that a blocked expansion valve does not cause higher than normal high side pressure. It actually causes lower than normal high side pressure. Okay? If you have a blocked expansion valve, and you go ahead and try and add some more refrigerant to the system, if you've got a little bit of refrigerant still flowing in the system, you're still putting a little bit of heat into the system, right? So if we haven't managed to pull the low side down to the point where the compressor shut off, that means we're still pumping a little bit, not enough to actually cool the system. So somebody might think it's just a low charge. And what do you do when you got a low charge? You put more in, right? No, you don't. You fix the system. You don't just keep topping it up, because we don't do that. So if you do somehow accidentally manage to get too much refrigerant in the system, what happens to the amount of liquid? Well, the amount of liquid starts to fill up your condenser. Okay, so now I've got liquid in my condenser, liquid in my receiver dryer, and I'm backing up liquid all the way through the system to the point where I've only got a tiny little bit of that condenser left to actually be a condenser. So if I use the condenser to store a bunch of liquid and I've only got, a couple of square inches of it left to actually be a condenser, how are we going to get rid of heat? We're not. And if you can't get rid of heat, that means that any heat you pick up starts to build up in the system. If you want to remember something, if there's a statement you're going to remember, I would say high side pressure is dictated by heat load. That's something you should remember. Okay? When I say heat load, I'm talking about the BTUs in the system. Okay? We need to have enough condenser space that's active so that we can take the liquid, take the vapor, turn it into a liquid and cool it down a little bit. Okay? If we run out of room to let this condenser be a condenser, then we don't have that phase change and we don't have any subcooling, and then yes, our high side pressures will spike. Okay? The reason for that heat load going up is because we're just not getting rid of the heat. The same thing happens when you physically block the outside of the condenser and you can't get air through it, right? If you can't get any air through the condenser, the heat builds up, high side pressures go up. Oh. Come on now. And if you can't get rid of the heat over on the condenser side, that means that refrigerant is still going to have all the heat in it, and it's going to be very difficult for us to do what we want to do over on this side. On this side, we do want some superheat. Okay. How much superheat do we want? Depends on the system. Probably somewhere, if you're thinking in Celsius, probably somewhere, 2 to 5 degrees Celsius maybe. In Fahrenheit, probably somewhere around 10-ish degrees Fahrenheit, give or take a bit. Okay. You want a little bit of superheat. Okay. And it has to be enough that you can measure so that the TXV can respond. If there's too little superheat, like I said before, expansion valve is going to close off. Too little superheat means it's too cold on the outlet. We're flooding the evaporator too much. Okay. Too much superheat means there's not enough refrigerant going to the evaporator. That might be because the expansion valve isn't open enough, and the other reason might be there just simply isn't enough refrigerant in the system. That's a way more common problem. Okay. Usually these systems leak out before the expansion valve fails. If you have a blocked expansion valve, you guys, you've brought this up. A blocked expansion valve is going to cause lower than normal high side pressures, and it's going to cause lower than normal low side pressures too. Because that expansion valve is acting like a restriction and the compressor is acting like a pump that's trying to suck refrigerant, right? So the suction side of that compressor, its pressure is going to drop down to the point where that low side switch is going to protect the system and kick it out. If I have an expansion valve that's blocked, how much refrigerant is going to be coming up around the backside there to repressurize and click that switch back on? Very little, if any, right? So that means that if you have a blocked expansion valve, refrigerant can't flow through here, so your compressor is going to click on, it's going to pull the low side down, then it's going to shut off, and then that's it. Okay? If the expansion valve is wide open, all right, because it's sensing a huge amount of superheat, because there's no refrigeration in this or refrigerant in the system, that means that the compressor is going to click on. Okay, there's not very much refrigerant in the system, so it's going to suck the low side empty, and it's going to kick off. But because the expansion valve is wide open, the pressure is going to equalize very quickly from the low to the high side. The compressor clicks back on. And you guys, a rapidly cycling compressor and a low charge, do those two things go hand in hand in your mind? It should, and that's the reason why. Okay. We're going to put some gauges on here. So for a high side gauge and a low side gauge, if we were to think about what the normal pressures for an operating system would be on the low side and on the high side. Okay. On the low side, probably between about 10 and 30 psi. Very normal. Okay. On the high side, some of you guys said you've done a fair bit of AC this summer. High side pressures, if it's kind of a moderate day, but you're still out there doing some repairs, they're going to be lower. If it's a really hot, humid day when you're out there doing your repairs, the pressures are going to be higher. Okay. A range, what do you think a normal range would be, just in your experience so far? Anybody? 150. Okay, on a cool day, I would say 150 is pretty reasonable. Just going to change my pen down a size here. Okay. Okay. As it gets warmer, that pressure gets a lot higher. It is completely normal to see something up to about 300, maybe even higher than that on a really hot, humid day. Okay. But anywhere between about 150 and 300 psi. Remembering, of course, like I said, heat load on the high side, that's what determines what the pressure is going to be. The higher the heat load, the higher the pressure. If it's higher ambient temperature, really humid, that's going to put more stress on the AC system. Your high side pressures are going to go up. Okay. Now, if I take a look at some of the tools I would use to work on this system, we're going to start off with our manifold gauge set first. So what we're going to do is somewhere over on the side here, I'm going to draw in that gauge set. Now, there's a couple of different styles. How many of you guys have gotten your own gauge sets so far? A couple of you? That's the shop's problem? Okay. So the gauge set the shop has, are they decent, or have they been around for quite a while? Been around for quite a while? Okay. So do those gauges, are you confident that they seal properly? Yeah? Okay. If you do have decent stuff, and if they keep on top of either maintaining or replacing the tools when they're worn out, air conditioning manifold gauge set is one of those things that they do not have a infinite lifespan. There's stuff in there that can wear out. If the valves start to wear out, or if the seals in the ends of your hoses start to wear out, you can't get a good seal anymore. How are you supposed to pressure test or leak test a system if your tools are just as bad as maybe what your system is? You can't. There's no way to know. All right. If you do decide eventually that the gravy work that air conditioning work is might be something you'd want to make part of your regular duties, get yourself a decent set of gauges. And the ones that you're going to want to get are going to have 4 hoses and 4 knobs on them. Okay. They do cost a little bit more, but honestly, if you start doing a fair amount of AC, you'd really appreciate having the options that having that setup gives you. So what we'll do first is we'll look at just a simple example. I'm going to draw this quick and dirty and erase it just so you guys can see. So you would have, for a normal AC gauge set, you'd have a hose with a valve and a gauge, another hose with a valve and a gauge, and then you would have this thing in the middle that gives you your third hose. That's what you have. Okay. And you can do most of what you need to do with this set of gauges, I'll be honest with you. Okay? But if you want things to be a little bit nicer, take that one, put it right there, and get yourself one of these guys. Okay? So this one's going to have 2 gauges. So your low side is going to connect over here to the low side service coupling on the system. The high side connects to the high side service coupling on the system. Okay. And then you're going to have a manifold in the middle of this. Okay, so that manifold is going to have a couple of hoses coming off of it. All right. And then each one of these has a valve. Okay. So we'll draw in our blue valve, our red valve. Okay. And then the other two each have their own valve. So this means that you can isolate and use, anything you really want here. Now, what would we possibly be hooking this up to? Aside from just hooking it up to our system to measure the pressures in there, the other thing we might be doing with our manifold gauge set is might want to vacuum the system out. Okay, before you vacuum a system out, what might you want to do to it? If there's still refrigerant in the system, there's something that we're legally obligated to do. Recover the system. Okay? Every system's empty when it shows up, right, guys? Not necessarily. If it's not empty, that means that we're going to have to recover. And when you recover refrigerant, what you're going to do is you're going to take a pump. Okay? That pump, that's your recovery unit. Okay? Now that recovery unit, what we're going to do is we're going to pump the refrigerant into a bottle, a recovery tank. So a recovery tank is going to be just a containment vessel here. It usually has 2 valves on it. All right? Those 2 valves on the top of your recovery tank, what do they usually say? Liquid and vapor. Okay? So your recovery tank is going to have a liquid line and a vapor line. Okay? And the liquid line is going to go down there to the bottom. So, liquid, vapor. Okay. So what I'm going to do is I'm going to recover the refrigerant. I'm going to pump it out of the system into the bottle. That bottle's sitting on a scale. Okay. Because I'm measuring how much I'm taking out of the system, and I measure that in pounds or kilograms or grams or pounds and ounces or whatever you want. I'm measuring the mass of how much I take out of the system. Okay. You'll notice right now, I don't actually have that extra hose on my 4-hose gauge set hooked to anything, right? Okay. So right now, I'm recovering. That means that this right here is a recovery unit. Okay. And a recovery unit is not the same thing as a vacuum pump. Okay. A vacuum pump, its job is to evacuate the system, and evacuating the system is not removing refrigerant, it's removing air and moisture. Okay. So my recovery unit, as it sits right now, I'm pulling refrigerant out of the system, and if I knew what my system capacity was and I measure how much I pulled out, I can actually check the charge level by doing this. Okay. Now, is my system going to be full of the refrigerant I think it is? Hopefully. Hopefully. Nowadays, that's not a very safe assumption to make, though, is it? When's the last, have any of you guys bought a bottle of 134 recently? Anybody here? Does anybody have any idea how much a bottle of it costs? if you're lucky. If I could find a bottle for $500, I'd be pretty darn happy. Okay. The last bottle I bought, of course, there was a core charge included in this, but I think it was closer to $800. Yeah, it's getting really, really expensive. Okay. So if you spend that much money, and then let's say you have a nice clean tank full of recovered refrigerant, do you want to contaminate that refrigerant with a bunch of who knows what that's in the system? Nope. So if you can trust what's in the system, then yes, go ahead and recover it. Okay, into your good 134 recovery tank. If you don't know what's in the system, then what do you do? Venting it to atmosphere is not the answer. Okay, you're supposed to recover it into a disposal bottle. All right. So when you have a disposal bottle of refrigerant and you recover into that, what you're supposed to do is take that back to your supplier and they incinerate it, and that's safer for the environment. Okay? So anyways, where or why would we have to do that? Why would refrigerant be contaminated coming out of a system, a closed system? What could have happened?
Red tech.
Good old red tech. Anybody can go and get their hands on that stuff nowadays. And they can pump it into a system, whether it needs it or not. Okay? Cross-contaminate refrigerant, which you're not supposed to do. And then it's your problem, and you don't want to get unlucky enough to cross-contaminate your good tank of 134. How many of your shops have a refrigerant identifier? So of course Tormont has one. Yeah, refrigerant sniffer. No, I'm not talking about a leak detector. I'm talking about a refrigerant identifier, and it'll tell you what kind's in there. Okay, perfect. Any other shops here have?
Pretty sure machine's capable of doing it with their AC machine. It has one built in.
A refrigerant identifier?
Yeah.
Okay. It might. That'll be your roll around in the shop machine, your big machine though, right?
Yeah.
Some of the new ones do come with an identifier in them. I wouldn't count on that being the case for the most part though. And if you guys have one, that is awesome. Okay. So then your other question for yourself is, well, if I don't have a refrigerant identifier, how am I supposed to know? Thing is, if you don't know and if you can't trust the customer, assume it's contaminated. Okay, put it in your junk tank. Now, it sucks when you're putting in refrigerant that is worth, realistically, what the customer is paying is probably close to $30+ a pound for it nowadays, and you're just going to throw that in the garbage. But it's better than cross-contaminating your own tank. Okay. So, anyways, you get your system emptied out. You do any repairs that you're supposed to do to the system. The next step that you would have to do, what is it?
Vacuum it out.
After any repairs, we are obligated to do a leak test. Now, is that going to be a vacuum test? Is it going to be a pressure test? Do we maybe want to do both? Okay. So I would argue that a pressure test is probably the next thing that we should do. What's interesting is sometimes a machine will hold under pressure, but it won't hold under vacuum. Okay. Or sometimes it'll look okay under vacuum, but it won't hold under pressure if it's got a small pressure leak. So I would argue that doing both is best practice. So I'm going to go ahead and put nitrogen in the system. And while I'm doing this, I am now currently done with my recovery unit. So I'm going to take this, I'm going to put it over here. Okay. Now, your nitrogen, how much should we put in? 150 to 200 psi. Okay. Now, a standing nitrogen pressure leak test, if you guys look back through the regulations that you were taught when you were doing your MOPIA training, I would have said that minimum 150 psi for a minimum of either 15 or 20 minutes it has to hold for it to be considered to have passed a leak test. I've worked on machines where they did pass the leak test according to that, and then you still get a call 2 weeks later that the thing's not working again, right? And that sucks. And that means that obviously there's a pinhole leak that you didn't find. Okay, so how do you find that?